Hello to all of you and welcome back to my SP2 channel. We are going to continue our discussion on the molecular orbitals for the diatomic molecules in period 2 with the focus on the 2s orbitals. Okay, so before we look at the molecular orbital, okay, I'm going to have a little bit of introduction on the importance of diatomic molecules. So these are small molecules made of two atoms. That's what we call them diatomic. And some of them are harmless, such as nitrogen gas. Some of them are very dangerous, such as carbon monoxide or even cyanide. They're actually very toxic, right? And some of them are pretty essential for our body, for our life, such as oxygen gas or even nitric oxide. Okay, so as you can see, they are tiny molecules, right? They're very small, but they can have a huge impact in our body. Okay, now let's take a look at the specific diatomic molecule, which is nitric oxide. This one is a very special molecule. I'm going to show you all of interesting properties of this molecule in our body. It is helping us with the blood pressure, relaxing our muscles. Very helpful for the immune system as well as the brain function, right? And what is interesting is back in 1998, there was actually a Nobel Prize winner, right? Specifically for the research that has been done on nitric oxide. Okay, cool, cool. Now, to understand the bonding in diatomic molecules, we're going to use molecular orbital diagrams. We're going to be focusing on homonuclear diatomic molecules where we have two of the same atom, right? And that is going to be specifically for period 2 of the periodic table. When you're looking at period 2, the atoms have 2s and 2p orbitals, okay? And here are the rules for the NO formation. Same number in, same number out. This means that the number of molecular orbitals that we are forming must be equal to the number of atomic orbitals that are combining. Next rule says similar energy works the best. This means that the atomic orbitals mix most effectively if they have relatively close energy. Better overlap, stronger bond. This means that the more two orbitals overlap, the more stable the bonding orbitals is going to be. And as a consequence, the less stable the anti-bonding orbitals is going to be. Okay, next one, 2 electrons per orbital. Each MO holds at most 2 electrons, right? And if I have 2 electrons, they should have opposite spin in order to follow the Pauli exclusion principle. And finally, when you're feeling your, degenerate or the one that they have the same energy, right? We need to fill them singly first, and then we can start pairing them up in order to follow the Holmes rule. Okay, excellent. Now, here's an example for lithium-2 molecule. As you can see on the left side, we have the atomic orbitals for our lithium, and then on the right side, we have the atomic orbital for the other lithium atom. So when you're looking at your lithium electron configuration, we're going to have 2 electrons in 1s, and we're going to have 1 electron in 2s. Okay, it's going to be the same thing for the other lithium atom. So 1s2, 2s1. Now, when you're combining your 1s electrons, right, or your 1s atomic orbitals, we're going to get these two molecular orbitals, as you can see here. We've got the sigma 1s and the sigma star 1s. I'm going to have 2 electrons over here, and the other 2 is going to be over here. Now, when you're combining your 2s with the 2s, we're going to get the sigma 2s here and the sigma star 2s. Now, when you fill your orbitals, I'm going to have both of my electrons here, and therefore my sigma star 2s does not have any electrons. This is an empty orbital. Okay, cool. Okay, now that we got the MO diagram, we can go ahead and calculate the bond order for this molecule. When you're looking at your bonding electrons, you've got 2 electrons in sigma 1s over here, and you've got 2 electrons in your sigma 2s. That means altogether we have 4 bonding electrons. The number of anti-bonding electrons is going to be 2. That's all I have here is my sigma star 1s. You take the difference between these two, 4 minus 2, right? That's 2 over 2, which is going to be 1. That means we have only one single bond between the 2 atoms in this molecule. Okay, cool, cool. I hope that makes sense to you. Thank you very much for watching this video. There's going to be one more video on the molecular orbital coming up soon, which is going to be covering the interaction between the 2s and 2p orbitals. Stay tuned for that.